Welcome everybody. I want to apologize because the talk is a bit technical and I know it's not the best way to start a rainy day. However, we will speak about multi-modal logic. It's a joint work with Camillo Fiorentini from the University of Milan and Ricardo from the University of Buenos Aires. Well, the idea of multi-valued modal logic is to combine the reasoning feature of multi-valued logic and modal logic. The motivation should be quite evident. And the way in which we can approach the problem is to try to combine multi-value semantics with the usual quick model semantics for modalities. Here, the first problem we have to address is what kind of algebraic semantic to choose for multi-valued fragment, multi-valued logic, because you have a different way in which you can interpret propositional connectives in the multi-valued settings. But there is in some way a natural choice, which is the one to choose Gödel algebras to use the interpretation of conjunctions as the minimum of the conjunctions. The conjunctions and the indication as interpretation. And the reason to choose semantics is that as proved by these guys in 2011, it is the only base you can use so to satisfy the normality principle, the normality axiom of modal logic. So if you want a multi-valued modal logic which in some way is correspond to the usual modal logic, you have to choose the fragment. To choose the interpretation. Formally, what we have is a quick model with a set of words and an accessibility relation which is weighted over 0, 1, and an evaluation function mapping every proposition at a range in 0, 1. And you have the usual interpretation of propositional connective based on Gödel algebras, while you can give a value to box-set formula and propositional formula, taking the infimum and the supreme over all the accessible word weighted on the accessibility relation. So in the case of box alpha, you have to put the value of RW with X implies AX alpha, and in the case of the diamond, the supreme over the conjunction of the two. The notion of validity is the usual one, always valid in N. If in every word its weight is 1. So starting from the notion of validity of the model, you can define the Gödel modal logic as a set of all formulas valid in all Gödel models. If you restrict the relation to be essentially the classical one, instead of weight over 0, 1, you take only 0 and 1, you can rewrite the interpretation of box-set and diamond formula as the infimum over the usual interpretation of boxes and diamond over crypto models. In this case, you have to admit that The value is 1 for a Boxer formula if there is no successor of W, and the diamond is weighted 0 if there is no successor of W. With such restriction, we call Gödel Modal logic the set of real value formula in these models. These two logics have been studied by Camillo, Rodriguez, Olivetti in several papers, and they have provided axiomatization for the boxed fragment of both logic. We have the suitability and the space for the boxed and diamond fragment, both in the free space and in the not free space. What we're making here is we also have a calculation for the boxed fragment. What left here is a calculus treating the whole logic, all the modalities at the same time. And there is a motivation in which we started to study a variant of crisp model, introduces a new restriction on the accessibility relation. We say that accessibility relation is weakness if every time in a world we have a formula with a modality is weighted L, and there is at least a successor of W, then there is a successor where the value of the formula K is exactly R. That is, we have a weakness for the value of the formula in the model. The exacting logic is the set of all formulas that are valid in our weakness of the crisp Gödel models. Here we have an example of a non-weakness model. We have from which we can assess an infinite number of word K. In every K, the value of the variable T is 1 over K plus 1. So you have the equilibrium of zero. So we have the box of P in W0 is 0, but there is no successor of W0 in which the variable has value 0. So this is an example of a model which is not weakness, and this is a crisp model, and this is an example of a formula which is falsified on such a model. The formula is box not P, implies not box P, and it's easy to see that the value of the formula is 0 on the root of this model. And it's also possible to check that on the other end, this formula holds in every weakness model. Indeed, this formula is 0 only if the antecedent is 1, holds 1, and the conclusion is the consequence is 0. But if the consequence is 0 following the red line, you have that the box P must be 0. The model is weakness, so you have a successor where P, the value of P is 0. This implies that not P is 0 in W1, and this implies that box not P is 0 in the root. So anytime you take this 0, this must be 0, and this proves that the formula belongs to the logic. This is an example of a formula which belongs to the GWC and not belong to CC. Since every instance model is a cruise model, we have that inclusion. So GWC is a professor at the University of CC. What we present in the paper is a calculus, it's a refutation calculus for logics. And for this calculus, we can do termination, completeness. We have a way to extract counter model for the proofs. We have a full circuit signal which does not require the tracking, and we can prove the dispensability of the validity problem for the logic. And we also have an implementation in a Java framework of the truth procedure. The idea behind the calculus is, it's a calculus works on constraints over labeled formulas. A constraint is a general constraint as is true. We have on the left a term which can be a constraint, sorry, a constraint over one, rational number, or a formula represent a model in the model. An atomic constraint is the same when you consider as level formulas only atomic formulas. The constraint have a general constraint on the left and an atomic constraint on the right. Atomic constraint on both sides. The entity semantics of constraints. Let us see the case, for example, of atomic formulas. We have that in 0.3 is greater or equal to 0.2 is the value, the interpretation of the value of propositional variable P according to 0 is greater or equal to the value of propositional variable 2 at the W0. This is the example of a complex formula. In this case, we are saying that this is true if there is a model where the value of this formula is less than 1. Given a set constraint, we say that the set is valid. We can find a model where we can assign to every label in the set of constraints a word of the model and every constant relational value in such a way that the resulting substitution are valid constraints. The calculus is calculus in the sense that when we prove a set of constraint gamma, there is no model subject the set of constraint holds in M. So we consider a constraint this kind, and we have the derivation for this constraint. There is no model for this constraint. This means that there is no pair of model. There is no model in the world such that AW is less than 1. This means that in every word the formula is 1, and so the formula belongs to the logic. In the calculus, actions are a set of constraints in which atomic constraint can be satisfied in the sense of that we can find the substitution of a constant and substitution, an assignment of rational values to constant and to atomic formulas, so that all the constraints are satisfied at the same time. We need to add some constraints, some more atomic constraints on box and then diamond formula, but is the technical, not so relevant. The important word of the definition is that consistency of an atomic set of constraints can be checked by a constraint solver over Q. So we can use a constraint solver to check consistency of relief over code. Well, these are the rules I only show give an intuition on behind the rule. The case of the rule for box. First of all, a rule is sound if anytime I can satisfy the conclusion of the rule, I can satisfy at least one of its premises. And here an example of the rule for box Lorentz. In the conclusion, I have this box formula, this box is constraint, and the rule gives us two premises. The last one, the last one corresponds to the case where R has no successor, and the right one is the case where R is a successor. The rule on the left substitute the formula with 1, and this corresponds to the fact that every no successor box of alpha must be 1, and so 1 less or equal to t is satisfied. On the right side, I have to consider the cable, the W as successor, so I introduce a new label, and I get rid of the box before A, and this semantic corresponds to the fact that I have a successor of W which satisfies the constraint alpha is 1 or equal to T. Well, the further side we put in paper is that the calculus is strongly terminating. There is a relation, a well-founded relational set of constraints which decrease applying the rules of the calculus backward. And so we get any backward booster strategy for the calculus terminates. The rules are invertible, so we don't need backtracking. And indeed, there is only one proof tree that can be generated. Obviously, we have a proof of the completeness, and the interesting point is that from every three proof of the calculus, we can extract a counter model for the formula of the root of the proof tree. This is an example. I wrote the branch. I cannot apply. There is no rule that can apply. The set is consistent. Consistency. Since it's consistent, the constraint solver gives me a solution, and I can give a solution to build the model. The labels represent words, anytime I will apply a boxed rule, I introduce a successor, and the final assignment give me the value, for example, W2 P is not 203. I set P equals to 0.3 in W, and this is a counter model. It's also easy to see that the model, the depth of the model is bounded by the size of the formula, and that also the number of possible successors of every word is bounded by the size of the formula. We can prove that the validity problem is in this page. This is not contained in the paper, but this can be proved using the same technique Villanova used for the calculus to be used as that was as the inspiration for our calculus. Just a word on the other results in the paper. We provided also a crypto-style semantics in the style of deterministic modal logics. There will be a relational semantic. We have an deterministic relation. We have a modal relation. The motivation for this semantics is that if we consider the propositional case, the non-modal case, we know that there is a correspondence between the semantic on probability norm and the semantics on linearly ordered critical models. We extend this correspondence to the modal case. The kind of abstraction we use is similar, is an extension of the one that was introduced for Gödel logics. Starting from a second word, we have a second cluster. Inside every cluster, there is a set of words which is ordered on the base of the values that propositional variable can take over the Gödel modal. In the semantic, we have to introduce obviously the relation between the intuitionistic accessibility relation and the modal relation, and we have these six relations, these six conditions in the style of Fisher-Sandwich condition model cryptoframes. Indeed, there are more conditions that in usually intuitionistic modal logic, but probably they are not only that we are studying if we can remove some of this condition. Future work, there is not an axiomatization of our logic, but there are axiomatization of Gödel and Gödel modal logics. So we are studying the possible axiomatization. We are extending the witness semantics to the fuzzy case regarding non-crisp Wittgen model. Rodrigo is studying, Ricardo is studying first order extension of new logics, and we are working on refinements. As I said, we want to remove some condition on critical frames. And that's all. Thank you.